This is a help video for the Laplace Impedance Simplification Game in Circuit Tutor. So I'll go ahead and enter that game. So the first thing we would normally need to do would be to go through the introductory tutorial on the website that would explain how impedances are found in the Laplace domain and how they can be combined to prepare us in order to work the game. So we'll skip that for right now. And now we have a choice of doing examples or exercises. And it's always a good idea to look at some examples here. So I'm just going to go ahead and generate one as an example. Okay, so we have three elements here that are in parallel. And you see that these are in the time domain because we have farads and henries for the capacitor and the inductor respectively, which never appear in the Laplace domain where we only deal with ohms. And we also see they're in parallel because they're connected to the same pair of nodes, colored black and red here respectively. So we'll go ahead and look for the solution to that one. So the first step here is going to be converting this into the Laplace domain using the formulas that the impedance of a capacitor, Z sub C, is 1 over the S variable times that capacitance, and the impedance of an inductor is S times L. This is very much like the formulas in the phasor domain that you may remember. In that case, though, S was just J omega. Here it's the full S, which is basically sigma plus J omega. So now, to convert this, the 8 farads becomes 1 over 8S using this formula here. The inductive 8 henries impedance becomes 8S ohms. And then the resistor is unchanged because its impedance is the same as its resistance. And now we are looking for the input impedance there. So we'll slide down here and we see that these have all been highlighted as being in parallel. And so to combine them, to combine impedances in parallel, 1 over the Z equivalent is 1 over the reciprocal of each of the 3 impedances. So we just take the reciprocal of the 6 ohm, the 8S, and the 1 over 8S. And in order to compute that, then these have been put over a common denominator. So here actually the 8S would be flipped upstairs, and then the common denominator would be 48S. So we'd multiply through each term as necessary to put them over that common denominator, and then take the reciprocal by flipping it upside down to get the answer, which is in this case 24S over 192S squared plus 4S plus 3, and that is in units of ohms. Okay, so now let's go ahead and work an actual problem. And we'll do this at level 1, or the easy level. So our first task, as in the example, is to convert our impedances. And we notice that first of all, these are all in parallel again because they're all connected to the same 2 nodes, colored black and red respectively. So we have an 8 Henry inductor, 7 ohm resistor, and 2 farad capacitor. So now to convert that, for the inductor, remember the inductive impedance is S times L, so that's just going to be 8S. So we just type 8S, or you could put S8 if you prefer, it doesn't matter, because of course multiplication is commutative. And then over here, we need to take 1 over SC, so that's going to be 1 over the quantity S times 2, or 2S, probably would be a better way of writing it. Notice, however, that it's very important that we use the parentheses here because this follows the standard PEMDAS rules of order of operations in algebra, namely that if you have multiplication and division, which are on the same level, those go left to right. So if we didn't have, for example, if I just show you taking out those parentheses, now what we're really doing, we're not taking 1 over the quantity 2S, but we have 1/2 multiplied by S, because S is now in the numerator since we go from left to right in the operations. And in fact, if I clicked out of that, it'll actually change the 1/2 fraction to 0.5. So anytime you type a fraction, it'll automatically evaluate that numerically for you just to save you a little bit of work. But that's in fact not correct here. That's not what we wanted. So we'll have to go back and change that to the correct thing, which is 1 over the quantity 2S. So it's very important, just as when you're using a calculator or any other calculating device, to follow the standard rules for order of operations, including, of course, the variable s. So that is the impedance there. And now we'll just click check impedances to see if that's correct or not. And it is. So now it will redraw the circuit for us using those impedances. So now we're in the Laplace domain because we have only ohms for all the elements, and we have the impedance shown. So we see again these are all in parallel. So we're going to first select these just as you would in any of the simplification games that you may have done before. So we just click on those, putting a check mark on all three. We could combine two at a time if you like, maybe use the product over some formula, something like that. I'm just going to do all three at once, which I think might be the easiest way to do it. So we have to combine those now. And so I'll click on the Combine Parallel Elements button, and it's going to ask me to put in the answer. Now, of course, you won't have any cheating advice there. So what I'm going to do is go ahead and compute that algebraically here. And so because we're in parallel, probably the easiest thing is just to add the admittances of these three elements in parallel and then take the reciprocal of that admittance. So the total equivalent admittance, Y equivalent, is the sum of the admittances of each element. So the admittance corresponding to an impedance of 8s ohms is 1 over 8s. And that, of course, the unit would be Siemens, although I'm not showing the units here for brevity. And then the reciprocal of the 7 ohms would be 1/7 Siemens. And then for the 1 over 2s ohms, the reciprocal of that, of course, would just be 2s, again, Siemens. Now notice these lowercase s's are the Laplace variable, not the Siemens. And also when you're writing, just be very careful to not confuse, for example, a 5 and an s, which is easy to do. So you want to make sure you make the s's small if you're doing this on paper. Okay, so now we need to combine these or add them, and we do that as with any fractions by putting them over a common denominator. So we identify the prime factors of each of the denominators. Here it's 2 times 2 times 2 times s. Here it's 7. And of course these don't really have any in common, so it's just going to be the product of those two. So it would be 56s is our common denominator that we have over here. And here we'd have to multiply, for example, by 7 over 7 to get that common denominator. So that gives us a 7 here. Here we'd have to multiply by the 8s over 8s. So that gives us 8s in the numerator with the corresponding same denominator. And the 2s would have to be multiplied by the whole 56s. And the 56 times 2 would be 112. And then we have s squared. And that's all divided by 56s. Now, of course, we can and should check to make sure we did that right. So for example, 7 over 56s, we see that's just basically 1 over 8s, which is what we had here. 8s over 56s is, the s's cancel out. In this case, it's just 1/7. And here, the 112 over 56 is the 2, and the s squared over s is the s. So that does indeed check. And now the equivalent impedance would be the reciprocal of the equivalent admittance. So I just basically flipped this upside down. And so I have 56s. And now notice in the denominator, I also made another change, which is necessary before we put it into Circuit Tutor. It will require, when you're entering algebraic expressions like polynomials here, that they be written in standard algebraic form, which means that you should put things in descending powers of s. So we start out with the quadratic term, then the linear term, then the constant term. If you enter it without doing that, it will simply ask you to reorder it. It won't count it as an error, but it's easier just to do it right the first time, and then that'll save some time. Okay, so I'm going to go here and click on this. And I'm just going to have the 56s. And then I'm going to put my denominator here in square brackets, or I could use parentheses. I'll bring that back up to remind myself. So 112s squared plus 8s plus 7. So I have 112 s squared plus 8. Oh, I'm sorry, squared plus 8s plus, plus 7. Okay, and you can use parentheses or square brackets to enclose the denominator, but they must match, of course, as you would always have. And notice for powers, we use that little caret, which you can find above the 6 on your keyboard, and so that would be the expression. Okay, this is what we call a rational function, and you don't have to factor this or anything like that, so this is a acceptable form of that. And we don't really need parentheses around the 56s because the normal order of operations would imply multiplying these things before we divide anyway, so that's not really a problem. Okay, so we'll check that. And indeed, that is correct. It's printed it on the screen for us now, and obviously we're done here. We have our single impedance, so we just say cannot simplify further. And of course, you could at any time, if you needed to, go back and review the introductory tutorial by clicking on that button. It'll take you back to the website. There's written help available. And let me point out also that in addition to the general help about entering things, it does have a special button down here. It says Rational Function Syntax Help. And that will bring up rules, as I mean, the ones we did just now are fairly simple, but it'll give you the general rules for entering rational functions in Circuit Tutor. And it'll show you, things that you cannot enter and things that you can enter, basically, and sort of tell you the different rules for that. Most of the time, you probably won't need to use this, and it will tell you anytime you make a mistake, basically what you're doing. But if you want to review this, that might help you learn to enter those things so that you won't have any problem. Okay. And anyway, that's accessed through the normal help menu in general. There's also, of course, the video help, which you're watching now, and you can give up at any point, again, for no penalty. And if you need help finding series and parallel elements, you can color the meshes or the nodes here. So we're done. And it did create a transcript here. And we can use that if we need to review or to study. Okay. Now I'm going to go and do a second problem here of a different type. So this time it's given us 3 elements in series, again with capacitor, inductor, and resistor. So once again, our first task is to convert from the time domain, where we have the farads and the henries, into the Laplace or complex frequency or impedance domain, where we have everything in ohms. So again, remembering that the capacitive impedance is 1 over SC. That's going to be 1 divided by, again, don't forget those parentheses, 3S, or we could write S3, it doesn't matter. You cannot, by the way, however, use negative exponents. If you use an exponent, that has to be a positive single digit. So if it needs to be in the denominator, just put it in the denominator, and then you won't have to use negative exponents. Then this would be SL, so that's just going to be 7S. And those are the impedances, so we'll go ahead and click on that, and those are correct. And now it's redrawn it, just using the impedances. And here we see all 3 things are in series because they're in the same pair of meshes, this mesh on the inside and the mesh on the outside. So we can just combine those all together. You could, again, do it 2 at a time, but there's probably no point. So we'll just do all 3. And then once again, it will ask us for the algebraic answer. So this time I'm going to, I'll just bring that over here. And so now we have to add the 3 impedances. So we have 1 over 3S plus 7S plus 1. And once again, we have to put that over a common denominator. Well, in this case, that's pretty simple. Of course, it's just 3S. So we need to multiply this by 3S over 3S. So that will give us 21S squared in the numerator. And this needs to be multiplied again by the 3S over 3S. So we just get 3S there. And again, we can check 1 over 3S. That's indeed what we had here. The 21S squared over 3S, of course, is just 7S. That's what we had here. And the 3S over 3S is 1. So we can easily check that, and it's a good idea to do that. And then here we don't need to take any reciprocal because that's already an impedance. So we'll just put this in the standard order with the highest power first, 21S squared plus 3S plus 1 all over 3S. And so 21S squared plus 3S plus 1. All over the quantity 3S. Now, once again, if I wrote 3S here, that's going to be incorrect because that implies that I'm dividing only by 3 and then multiplying by S. So once again, very important to use parentheses around the denominator. Notice I also had to use parentheses here around this numerator, because if I left those out, for example, I'd only be dividing the 1 by the 3s, which is not what we want. We need to divide the entire expression. So again, use of parentheses or brackets here is crucial to get the thing that you're actually expecting to get. And there it's shown in the build-up form while it records it. And that's correct. So now we have basically solved that problem. And once again, we just say can't simplify further. And it once again stores a transcript. And that finishes this level. And if you want to go back and look at your transcripts on any level, of course, you can click this review work button, and that'll just bring up your transcript files, and you can open the ones that you just created.